When Ford executives decided to bring back the GT, one of the most iconic, best-loved machines, they knew they'd be judged by the past. But things have moved on. The new car needed to be modern and more efficient. Engineers did something unthinkable for an American supercar. The Ford GT is powered by an engine that started life in this, a truck. And it's not even a V8. You just don't do that. A generation ago, this would have seemed ludicrous. But thanks to extensive re-engineering, redesigned airflow, and testing at the very limits of performance, this engine went from hauling hay to hauling ass. The original Ford GT40 won the 24 Hours of Le Mans race 4 times in a row, from 1966 to 1969. Its large displacement V8 engines, up to 7 litres, proved reliable and powerful, and allowed the American newcomer to punch Ferrari in the nose at the world's toughest race. Fast forward 50 years, and Ford's engineers wanted to make a car to take that trophy again, to mark the glorious anniversary, and anything less than a win would be embarrassing. So a small group of engineers gathered in a basement, keeping the project a secret. Everything about the GT had to be developed undercover as an internal skunkworks project. Unlikely as it sounds, its engine is based on the V6 in the F-150 pickup truck. That hardly screams supercar, but the 3.5-litre V6 had already been proving its mettle. The Ford F-150 is America's best-selling vehicle, but truck buyers like their traditional V8s. So to prove a powerful V6 was tough enough, Ford ran it in the grueling Baja 1000 desert race in 2010. But there's a long way between a desert race in an F-150 and the 24 Hours of Le Mans in an all-new GT. In 2013, Ford started tweaking the engine for more power to run in the Daytona Prototype Endurance race series. It needed to take an engine designed to develop 365 horsepower in a road vehicle and nearly double it for a race car. The company ran the engine in dynamometer test cells. This basic but crucial engine research is needed to optimize fuel and airflow and harness the most power possible.
So this is it. This is the engine. This is the 3.5-litre V6 twin turbo here in a rig. Now the engineers here are going to give it some boost. The turbos are on the side here. They're going to really rev it up. They're going to see what this engine is capable of. If you think it's loud now, it's about to get really noisy in here, so we'll watch from outside.
Using dynamometers allows engineers to be even more cruel to an engine than a racing driver is, running them at high load and revs for 24 hours straight or more. Here you can see the heat pumped out, making the exhaust glow bright red. Engineers have come up with some ingenious tools to help them figure out what's happening inside a running engine. At its most basic, fuel and air is ignited with a spark. But when you're trying to get every drop of power from that fuel, how it spreads, if some gets trapped in corners of the combustion chamber, if it doesn't mix well with air, all of that matters. And it all happens in just fractions of a second. What's
Critical for those performance engines is that you need to get all the power output that you possibly can from that air that you're inducting. So if you're going to downsize to a V6, you need to turbocharge. If you're turbocharging, you need to be, and you want to get all the power output out, you need to make sure that the fuel and air are mixing properly and the combustion is taking place rapidly and efficiently.
To watch the combustion process, engineers can use an optical engine. It's see-through, so with a high-speed camera, they can watch the explosion happen in real time. It's in dynamometers that engineers were able to prove the concept of downsizing, that a V6 can do the job of an old V8, both for race cars, but also for the cars that are sold to regular consumers. This type of fundamental fuel-burning science is what helps engineers develop better engines. Ford had proven the 3.5-litre V6 turbo engine in testing, in trucks, and on the track. It was time to start customizing it to compete in the toughest endurance race of all. Once the development of the Ford GT was no longer a secret, engineers could get to work building a machine to win the 24 Hours of Le Mans race, 50 years after the GT40 smashed it. This early prototype allowed them to start proving some of what they'd figured out in the labs and on computers on the track. It's rough and ready and full of cables and loose parts, but the GT DNA is already showing through. Combustion takes more than just burning fuel though. It takes air too, and lots of it. The smaller V6 engine needs turbos to develop that insane 600 plus horsepower from 3.7 litres. Turbochargers compress air to squeeze more into the cylinders. More air equals more fuel that can burn equals more bang.
So on an engine, the key to performance is all about airflow. And that's why we talk about engines in terms of their displacement. You might talk about a 5-liter Mustang, and that's how much air it can draw in every 2 revolutions of the crank. When you turbocharge an engine, you've got an active device that allows you to push extra air into the cylinders. So we can make this 1-liter engine look like a 1.5 or a 2-liter engine, so it feels like a much larger engine. So we're trying to operate right at the stoichiometric, or right at the perfect amount of fuel for the air that's available. And so by using a device like a turbocharger to push more air in, that allows us to inject more fuel at that same ratio and then get more performance.
In the Ford GT, it wasn't just a case of slapping on turbos. Designers across Ford had to work together to help this engine breathe. First, using computers where modelers smooth the flow in the inlet manifold, the air pipes of an engine.
You see here, the curvature here is make sure we have least amount of the pressure drop, basically the resistance.
And then to the 3D printing lab for some rapid prototyping.
Initially, to get a one piece or an intake manifold, you have to create what's called a tooling package, which goes to an injection molding house, which is 3 to 6 months of development. We can turn these around in 2 to 3 weeks.
Finally, the engine itself was perfected. It was time to start integrating it with the car. The Ford GT's engine is behind the driver, which gives excellent weight distribution, but makes it a challenge for the designers to come up with unique ways to get air back to it, to feed the sucking, howling turbos.
The buttresses, there's actually cooling in the buttresses that put the radiators outboard where they need to be. We really shrink wrap those functional pieces to come up with something that is going to be great on the racetrack in terms of air management and aerodynamics. As we kept shrink wrapping the cabin and the engine, we started to develop almost a teardrop shape in the fuselage, hence developing the buttresses, so we actually disconnected the rear fenders from that teardropped fuselage. So it really helped us in the wind tunnel.
The car was becoming real rather than just a collection of parts, but it still needed a few engineering tricks to fit it all into that beautiful shape.
So what have you had to do to deal with the size constraints that you have here? How do you fit a large engine that was originally developed to go in the hood of a truck in the back of this car?
One of the obvious things that you can see is the fact we have a dry sump cooling, dry sump lubrication system.
Is that what this is?
That's what this is. That is the reservoir tank. The system holds approximately 15 quarts of oil. There's a scavenging pump which pumps oil from the engine into this recovery tank.
And let's just break this down to basics before you go on. So the sump is the thing that sits normally underneath an engine that captures all the oil as it kind of drips down to the bottom, and then it gets recirculated back round. That's the bit where they unscrew the bolt out of to drain it when you have an oil change.
That's correct.
You've scrapped all of that, so you've kind of got rid of that from the bottom of the engine and moved it to this tank here.
Correct, and that allows us to drop the engine lower in the car, lowering the center of gravity, making it a more compact design.
But just as engineers were feeling confident about entering their new Ford GT in the 24 Hours of Le Mans with its new downsize engine, they realised they had another problem. The modern, sophisticated computer control introduced an issue. Race engineers usually program car computers with valve timing, turbo boost, fuel injection, everything that it needs for maximum power, using data gathered by trial runs at a racetrack. But Ford didn't have that data, and it couldn't go and run a lap or two at Le Mans to figure out how high the engine would rev or when the driver would call for wide open throttle. They had nothing to map the car's computer with. So they turned to simulation, sophisticated video games. At a driving simulator in North Carolina, Ford ran virtual laps of Le Mans and used data from that to do the initial tuning of the car's engine. When the GT finally hit the track, it was the first time all the computer simulations, the modelling, the prototype 3D printing, and the hours and hours in dynamometers would be put to the ultimate test. And number 68 came across the finish line in first place, and the team also took third and fourth. The gamble on downsizing had worked. The V6 proved itself, and much of what went into making the race car ended up in the GT Road Car too. And it's not just supercar owners who benefit. The downsizing technology is making its way into more and more regular cars. So the next time you hit the gas, you can thank the efforts of engineers for the performance that you get.